Today, I want to prove that f is injective if and only if f of a intersect b equals f of a intersect f of b, where a and b are subsets of x. So let's go ahead and do the forward direction of this proof. So we're going to first start off by saying assume f is injective. Okay, and what are we trying to show? Well, we're trying to show that f of a intersect b equals f of a intersect f of b. Now, in order to do this, we need to show that f of a intersect b is a subset of f of a intersect f of b, and vice versa. So let's start with that first inclusion. So let's start off by saying notice that f of a intersect b is a subset of f of a. Now, why can I go ahead and say this? Well, by definition, any element of A intersect B must be an element of A. So the image of A intersect B must be a subset of the image of A. Again, because any element in the intersection here must be an element of A. So we can go ahead and do the same for f of b as well. So we'll say and f of A intersect B is a subset of f of b. Okay, and then this actually leads us to our first inclusion because f of a intersect b is a subset of f of a and a subset of f of b. So by definition, it must be a subset of f of a intersect f of b. So we'll say then f of a, oh wait, I should say f of a intersect b is a subset of f of a intersect f of b. Perfect. Now we're going to go ahead and do the converse inclusion, which is that f of a intersect f of b is a subset of f of a intersect b. So let's start off by saying let p is just an arbitrary element, let p be an element of f of a intersect, that looks like a logical and symbol, let's say intersect f of b. Okay, what does this mean? Well, this means that p is the image of some element in A and the image of some element in B. So we'll say then p equals f of A equals f of B, where lowercase a and lowercase b are elements of uppercase A and uppercase B. Perfect. So this is just saying that p is the image of some element in A and the image of some element in B. And now we're going to go ahead and use the fact that f is injective. So f being injective means that f of a equals f of b implies that a equals b. So let's say that. We'll say by our assumption f of a equals f of b implies that a equals b. And notice that a and b are from different sets, but they're the same element. They're equal. So they must by definition be a part of A intersect B. Okay, so what have we done here? Well, we had some arbitrary element P in the set f of A f of A intersect f of B, and we showed that P must be the image of something in A intersect B, which is exactly what we wanted to show. So we can say, therefore, f of A intersect f of B is a subset of f of A intersect B. So we just showed both inclusions. We showed that f of A intersect B is a subset of f of A intersect f of B, and then we showed that f of A intersect f of B is a subset of f of A intersect B, which means that the sets must be equal. So we'll say we can then conclude that f of A intersect B equals f of A intersect f of B. Perfect. And this is actually the entire forward direction of the proof. We assumed that f was injective, and then we showed that these two sets were equal. So now we need to do the other direction of the proof. And we'll go ahead and do that down here. So we're doing the backwards direction of the proof. So now we need to assume that f of A intersect B equals f of A intersect f of B. Okay, so let's go ahead and start this off. We want to show that f is injective based on this fact. So let's say let x1 and x2 be elements of X such that their images are equal. So we'll say f of x1 equals f of x2. Okay, so x1 and x2 are elements of X and their images are equal. Now, what can we go ahead and say about this? Well, let's try to bring it back to our assumption right here. We'll say then f of x1 intersect f of x2 must be non-empty, right? Because the image of x1 and the image of x2 are the same, so their intersection cannot be empty. So we have that the intersection of the images are non-empty, and then now we can go ahead and use our assumption. So we'll say by our assumption, so by our assumption, f of x1 intersect f of x2 equals f of x1 intersect x2, which is not equal to the empty set. So we can actually make another conclusion from this. So the image of the intersection of x1 and x2 is non-empty. So this actually implies that x1 intersect x2 is non-empty, right? Because if x1 intersect x2 was empty, then we would be mapping the empty set to something non-empty, which isn't possible. So that implies that x1 intersect x2 must be non-empty, and this actually implies that x1 equals x2, right? Because if x1 intersect x2 is non-empty, that means that x1 and x2 must be the same element. And we've actually just shown that f must be injective, right? We let two arbitrary elements, x1 and x2, be contained in X, and they had the exact same image. And then that implied that the two elements were equal because of this assumption we made. So, and that's the exact definition of what it means to be injective. So we can say, therefore, f is injective. And that actually completes the backwards direction of the proof. We assumed the set equality, and then we showed that f was injective because of that. And that is the end of the proof.